Hello, this is Jean-François from Calray. Thank you for joining me in this session about high-performance RoCE solution for end-to-end NVMe communication. What about the abstract here? It's very simple, right? We want to go through SSD technologies and specifically spend some time on explaining a use case we have been working on here at Calray for a while, disaggregating HCI architectures, right? Explaining the value about NVMe UF and why we need another alternative. This is about me. I've been in the industry for a while, involved in the different organizations such as SNIA and NVMe. So if you want, please reach out to me. If you have any question, I will be more than happy to answer your questions. So let's see why NVMe is pushing boundaries. I've been in this industry for a while. And when I started with those architectures, I've been suffering with my customers about HDD weaknesses and specifically performances, high latency versus application requests, right? Application were demanding millisecond response time, where HDD were delivering tens of milliseconds with very low number of IOPS. And you see the maximum we got here was like 300 IOPS. So all the techniques the vendor were implementing at that time were big cache, right? Those big cache from vendors like Hitachi, EMC, or Famous, right? This was the only way to ensure the right response time to applications. So really at that time, pressure was on drives. Then came SSDs. What happened? SSDs, the first generation SSDs, were able to deliver 30K IOPS. At that time, I was doing a lot of benchmarks, and we had to rewrite all our benchmarks using serial benchmarking to parallel benchmarking because SSDs are parallel devices, right? So it put a lot of pressure on the storage OS, and many of them have had to be rewritten. And some startup raised like Pure Storage with really a new type of OS taking benefit of SSDs, right? But it put a lot of pressure on many vendors. And again, it put some pressure on the application, but not that much. Really, we see the bottleneck. We saw the bottleneck here, and this is still the case today, right? SSDs, SAS SSDs have started really to change the perspective and to provide sub-millisecond response time to applications. So this is really interesting. So pressure still today is a lot on the storage OS. What's happening next? We start to see NVMe SSD. So NVMe, that massively parallel protocol, is changing the game. NVMe SSD is the first generation taking benefit of PCI Gen 3. PCI Gen 3 can deliver nearly 500,000 IOPS, right? Just think about it. If you have 24 SSDs, that generation, delivering each of them 500,000 IOPS, the full array is able to deliver 12 million IOPS. If you take a storage controller compute node, the most powerful of them is kind of sustaining 2 million IOPS, right? So 12 million IOPS on one hand, 2 million IOPS from the compute node or storage node perspective. You need a bunch of them to saturate your storage device, right? So what's happening? That generation of SSD start to put pressure, nonetheless, on the storage nodes, but on the application nodes as well, right? You need parallelism. You need to rewrite your applications. And some of them are already ready for that, like containers, because they are massive parallel objects, right? Think about the next generation SSD coming as well. PCI Gen 4 SSDs, they will deliver, or they are delivering already today, 1.5 million IOPS. This gives about 14 million IOPS from 24 of them. This is really changing the game. This is putting the pressure up the stack, up to the applications, up to the way you develop and you think about your application, right? So it's a really NVMe, NVMe, and OF, really a new paradigm here in the architectures. So yes, we see that transition. It's a bit slow, right? Because it's a massive change, but definitively NVMe Express NVMe OF are those new protocols to take benefit of those new drives and to deliver top application, tier 0 applications, the best performances ever. Again, and the other paradigm is massively parallel. And that's why at Calway, we are best fit here because we have a massively parallel device, massively parallel processor. So the two combined makes a good fit. So we've seen the benefit of having NVMe drives at the node level, server level, compute node level, and we have seen many of those benefits already. What is starting really to ramp up is the fact that now you build a fabric with storage arrays which are NVMe OF ready, leveraging NVMe devices 100%. So it's really 100% NVMe down the stream from the application down to the drive, massively parallel access. So we see the promise here of a big change for communication in the data centers. There are many protocols for NVMe OF, many ways to change things, right? You may know fiber channel, you may know IWARP. What I'm going to focus on here, because I think those two most leverage with Ethernet fabrics are TCP and RoCE. And at least at Calway, we spend more time on delivering those two, right? You have to make a choice. The big difference between them is really performance. RoCE or DMAs is going to be fast, right? However, you need specific components in order to have a RoCE fabric. Even if it's leveraging your Ethernet components, you need specific switches, specific parameters, specific NIC, right? So for common things, if you want to reuse your architecture, you're going to go to TCP. You're going to get very good performance, but you're not going to reach the top. If you want to consider HPC and top application, tier 0 application, you may consider RoCE, even though if you have to have specific component for that. And you see here like a mapping of the application, illustrating what I just said, right? It's a trade-off, right? Obviously, for many of you, right, TCP will fit. For some of you, reaching really the top performance, you need to consider RoCE for some of your applications. Let's focus here some time about what we have been working on at Calway, which is really trying to disaggregate the architectures, leveraging NVMe OF, and trying to build those composable architectures we have been looking for a while. So if we consider our HCI clusters, right, you have a bunch of nodes, right, made of compute, storage, and network, all interconnected with a Ethernet network, 10 gig for most of you, right? What's happening? You create a VM, you create a container, and obviously you have some data associated with that application. They both reside at the beginning on the same node. But in real life, applications are moving. First, because the nodes are fully loaded and you need some power to have new applications, or your application is increasing, and you have to move it to a node which has more power to host your application. So you move your application. Obviously, moving this application will use interconnect and will load that interconnect. And by moving this application, while not moving the data, you create dislocation, right? I don't know if it's correct, but you have a problem here because your data reside on one node and your application on another node. And you will use the interconnect in order to reach the data. So you're going to burn cycle for your x86 because your x86 is managing the network stack. You're going to burn x86 cycles because it's managing the storage stack, and you're going to burn your internet interconnect because this is where you're going to access your data across the cluster, right? So a lot of bottlenecks over there. This fragmentation is really a problem. So in order to avoid that, what you're going to do is really relocate your data. And relocating your data, again, you will have to transfer your data through the interconnect, through the cluster interconnect, again, and you create an overload here. So really not efficient in terms of managing your sets, even if it's very simple to manage. So, and what is NVMe OF provided here. So first is trying to remove those boundaries by creating a global repository. You can share your local drives as if on the network, right? So you can build an hyper-converged infrastructure with some nodes with data, with some nodes without data or without drives, and with some NVMe storage arrays. So really you create a global data repository. So you will never access your data across the cluster interconnect, but you will use that specific network. That's where, even if you consider RoCE, switchless architectures we have been working on at Calway are very powerful because you don't need those RoCE, very expensive RoCE switches, and you get the full performance. So you create that global data repository. So when you create your application, and when you move your application across another node, sure, you're not going to burn your Ethernet interconnect to access the data, but what remains is the fact that everything is managed by the x86, right? x86 is overloaded. x86 is managing the storage stack. x86 is managing the Ethernet stack, right? Plus your application. So you're using a lot of x86 cycles in order to manage those things, data movement across, application movement, data access, etc., etc. So it's not ideal, right? It's the first good step to give you some more flexibility, but you need to move to the extra to the extra mile. Makes another difference, and this is what we have been working on at Calway. What we are doing is we are building a target initiator NVMe smart card. This smart card is nonetheless creating that global data repository, but it also take power on the drives. So we remove the storage stack from the x86. We take control of the data completely, right? So we free the x86 stack completely from the data management. So let's take what's happening when you create an application. Same here, no change, completely compatible. Now, if I move my application across to another node, nonetheless, I don't have to move my data back to that node because I will access through that data network my data residing on the first node it has been created on, right? Second, because the card is managing the storage stack, you do not use x86 cycles in order to manage that storage access. We also offload NVMe OF. We terminate TCP and RoCE sessions, so you do not use x86 for network as well. So you will decrease here your x86 load by 20 to 30% minimum because you completely offload Ethernet stack, storage stack, creating that global data repository. So you can move your VM around. You can expand your global capacity without disrupting your application. If you move your VM, you don't consume cycles. You don't need to move data around. This stack is a shared array, but you use your standard components. Really here, a powerful implementation. No more data migration required here for that environment. So at Calway here, we spend a huge amount of time in building those architectures, leveraging those new protocols, NVMe, OF, TCP, and RoCE. We are doing disaggregation. We are building composable architectures as simple as if you had an HCI implementation today. We have 64 cores in the data plane for each processor in each card. This allows us to run average coding line speed. So you can combine offloading your storage stack as well as offloading your data services, right? And we are compliant. Right? We have just announced our compliance with NVMe OF. So this is really interesting in terms of startup organization and startup compliance. So again, a lot of good things here coming. Good knowledge, good perspective, leveraging NVMe OF, but not just NVMe OS. So please reach out to me if you have any question. Thank you for your time today. Appreciate that. And looking forward to your question and our interactions. Bye-bye.